Let's have a look at our circular motion unit assignment, starting with question number 1. It says a 1,200 kilogram race car makes 3 revolutions around a circular racetrack of a radius 300 meters in 2.50 minutes. Determine the centripetal acceleration and the centripetal force. One thing that we want to draw attention to, of course, would be what? What's one thing that would quite likely, in some cases, lead us to a silly mistake even? Minutes, yeah. We want to convert that to seconds. We also have to remember here we've got 3 revolutions around a racetrack in 2.5 minutes. That doesn't give us the period or the frequency per se, but we can find the period or the frequency from that fairly easily. Let's write down a few givens here right now, and then we'll go from there. We've got a mass of 1,200 kilograms. I'm going to say that the radius of the circle is 300 meters. I'm going to say that the number of revolutions, or the number of cycles, whatever you want to call it, is 3. And we're going to say that the time here, the time is 2.5 minutes, which I'm going to multiply that by 60 to get seconds, gives me 150 seconds. I want to find the centripetal acceleration. I'm going to say A is equal to V squared over R. Of course, it's A is equal to V squared over R. Everybody did that. I think every single person in both classes wrote down A is equal to V squared over R. But, of course, I'm missing V. How am I going to find V here? Lots of you guys got this. What am I going to do? Tina, what am I going to do to find V here? Good. V is equal to 2 pi r over t. Now, I don't know what the period is. I don't know what big T is. So, Ben, what am I going to do to find big T? Well, I could just say T is 1 over f. Sure, I could. But I don't know what the frequency is either. If you're going to find the frequency from the stuff that's given to you, you might as well find the period directly from that as well. Tiana? Yeah, why don't we just say T is equal to the time, which is 150 seconds, divided by the number of cycles, which is 3. So the period ends up being 50 seconds. All right, Ben, if we had went 3 over 150, then we would have got whatever, 0.02, and then we would have said T is equal to 1 over f, but we might as well go straight to the punch and get T right away, okay? So 50 seconds here, V is equal to 2 pi times R, which is 300 meters, divided by the period of 50 seconds. V ends up being equal to 37.6991 meters per second. And then we're going to turn around and sub that into this equation, 37.6991 meters per second divided by R, 300 meters. Now, this is one thing that I noticed throughout this assignment that a number of people forgot to do. Forgot to square something, right? If something says V squared, then square it. Okay, you write that down in the equation, and then you forget to do it when you sub your numbers in. Okay, when we do square that and divide it by 300, we end up getting a centripetal acceleration of 4.7374 meters per second squared. Now I'm going to round that to 4.74 meters per second squared. Anybody want to take a stab at why I wrote down the unrounded number? I didn't really need to, right? But why did I write it down, Venture? Yeah, since there's a B and a C, I want to write down that unrounded number in case I might use it for B and C, right? You guys know the deal, right? Round it to 3 significant digits here because that's what appears in our data. But if we're going to use that number later on, we have to use the unrounded number. So let's just write it down in case we need it. We may or may not need it, but just in case. Remember, I did not take off significant figures for the assignment here. And unless you messed up a lot on units, I didn't take off marks for units either. But that kind of stuff does get zinged tomorrow, right? So this should be 3 digits. If you made this 2 digits or 4 digits, then you're going to lose a half a mark for that tomorrow. Or if you forgot the units, meters per second squared, and that was a fairly common thing, to be honest, was forgetting units, then you're going to lose half a mark every time you forget units as well. All right, centripetal force. What do you want to do for centripetal force? Some people went back to the start, back to scratch and started from scratch. Some people took a little bit of a shortcut, like I did. Haley, what do you think? What did you do for finding the centripetal force there? Okay, perfect. That's not exactly what I did, but that is absolutely perfect. It's a valid equation. You have m, you have v, you have r. Why wouldn't you do that, right? Hey, you sub your numbers in there. What do we got here? 1,200 kilograms times the speed, which we found a minute ago, 37.6991, but we have to square it, divided by the radius of 300 meters, and we get a centripetal force of 5.68. We'll say 5684.892, just in case we have to use it later on in question C. But we will round it to 3 digits here, 5.68 times 10 to the 3 newtons. Good. So Haley's answer is just as good as my answer. But what's the shortcut here, Ethan? Yeah? We could just say F is equal to m times a, right? If we said F is equal to m times a, we've already found the acceleration in question A, 4.7374. So 1,200 times the acceleration is going to give us that centripetal force. Does that make sense? Either one is fine. Hey, this way, the way that we showed here, the way that Haley showed, the one small disadvantage of that is that it's a little bit more work, and it leads to a bigger possibility of making a mistake, right? Because if we forget to square v, then, you know, or something like that, calculator entry mistake. But as long as you do that correct, it's just as correct as my method. Ethan, you had a question?
I was just going to ask what your way was.
I'm sorry?
I was going to ask what your way was.
Okay. My way is quicker, but not better. Okay, quicker, but not better. Now, we want to find the coefficient of friction between the cars and the pavement. This is also pretty well done. For the coefficient of friction, we're going to say FC is equal to FF. The centripetal force, some people went and said mv squared over r is equal to mu times the normal force, which is fine. But we already found the centripetal force. It's 5684.892. So that's what I did. Okay, I wrote down the number that I already had calculated, equals mu times the normal force, or mu times m times g. M was 1,200 kilograms, and g is 9.81. Now, this is one of those situations where the normal force is equal to gravity, right? It's countered by gravity, and it's equal to gravity. So we saw from mu there, 1,200 times 9.81, take that over by dividing, and we get 0.483. So 3 significant digits all throughout. Don't forget the significant digits. Don't forget the units, meters per second squared, newtons, and no units for the third one. Okay, no units for the third one because it's really force divided by force. Newtons divided by newtons to cancel. Question 2. 1,200 kilogram roller coaster car is moving around a vertical circle loop of radius 12 meters. It's the minimum speed that the roller coaster needs to move so that it does not fall out of the loop. It's going to fall out. Where's it going to fall out? Ariel, where's it going to fall out if it's going to fall out? Yeah, it's going to be at the top. Right? You're never going to see a roller coaster fall out of the loop or anything fall out of the loop at the bottom, right? So it's going to be at the top. Let's draw a free body diagram for the top of the circle. We'd say FG acts down and FN acts down, at least usually. Why did I say usually? Why did I say usually FG and FN act down? Why usually, Dylan? Okay. Yeah, wait. Okay, at the bottom of the circle, Fn acts up, absolutely. But at the top of the circle, Fg always acts down, and Fn usually acts down. Why did I say usually? Yep. Good. So in this situation, for minimum speed, it's equal to 0. So it's not acting up or down, right? It's just 0. There is no normal force. Not every time you're at the top of the circle. Most times you're at the top of the circle, there is a normal force, and most times it acts down. But when you're looking for that minimum speed, it's 0, so it disappears. All right, Fnet is also equal to mv squared over r, and of course Fg is m times g. M's cancel. Looking for v. R is 12 meters. Now, technically that term is negative because it's downward. equals negative 9.81, but the negatives end up canceling because it's in both terms on both sides. Take the 12 up by multiplying, and then we're going to square root, and V ends up being 10.84988 meters per second, which equals, in 3 digits, 10.8 meters per second. Now, some of you said 10.9 meters per second, and I marked that correct, 10.9, because I see exactly where that came from, right? 10.8493. Okay, if you take that one, and it rounds up to 10.85, and then 10.85 rounds up to 10.9, right? Is that proper rounding? No, like I see the logic in that, but you got to look at, if we're looking at this digit as being our final significant digit, then we got to look at the digit right after that. The digit right after that is a 4. It doesn't matter if there's a 9 after it. It doesn't matter if it's 10.84999999999. Okay? If the digit right after the 8 is a 4, it rounds down to 10.8 meters per second. Again, I didn't zing you for that this time, but on the test, I would. That's not what I was trying to see on this assignment. But of course, on a unit test, that does get zinged. Now, once again, why did I write down the unrounded number there, 10.84988? Just in case, right? Just in case. Jacob, just in case what?
You need it in B.
Yeah, just in case I need it in B, or C for that matter. Okay, B says determine the force of the track acting on the roller coaster if the car is moving at twice the minimum speed. So we're going to say for this one that V, twice the minimum speed, is 21.6998 meters per second. And at the top of the circle, we have those two forces, Fn and Fg acting down. And we're going to say F net is equal to Fn plus Fg. This is always what we do. When we have more than one force acting, we say F net is the sum of the forces. And these are always the same two forces that we have in a vertical circular motion problem. Now, what's F net also equal to? What's F net also equal to? Megan, Fn plus Fg, but also, what?
Do you mean like on the other side?
Yeah, what do we sub in for F net there? Good. It's the centripetal force. Fn plus, and Fg is mass times gravity, mass times 9.81. So we start subbing in some numbers here. We say 1,200. Once again, don't forget to square the V. The unrounded value of V over R, which was 12. And I ran out of space there. Now, we got to pay attention to negatives here, negatives and positives now that we sub numbers in. The centripetal force, McKenna, the centripetal force when we're at the top of the circle is which way? Towards the middle. Yeah, where is the middle relative to you? Down. So we're going to make that centripetal force, now that we've sub numbers in, negative, right? Alexis, the force of gravity is always going to be which way? So it's going to be negative as well, right? So we calculate that number on the left-hand side. Write it down. I'm not sure what it is, because I didn't show that in my own work here, but it's something. 1,200 times negative 1 is also something, a number, but it's negative. Now, how do we take this negative number on the right side over to the left side? Christian, how do we take this one over to the left side? Right. Take it over by adding. And when we do that, we get a normal force, which is really what we're looking for here, right? The force of the track, the normal force. I get negative 3.53 times 10 to the 4 newtons. If you didn't get that, make sure that you can get that by rearranging that. Now, not a lot changes when we're at the bottom of the loop. Just the direction of our forces here. Once again, F net is equal to Fn plus Fg. mv squared over r is equal to Fn plus mg. We're going to say 1,200 again times 21.6998 squared again, divided by 12 again. 1,200 times 9.81 for the force of gravity again. Let's worry about signs here. Gravity is always going to be down. Nick, which way is the centripetal force this time? Yes, because you're at the bottom of the circle, and as McKenna said in the last question, it's towards the middle. The middle is up relative to you, so it's going to be a positive number. So we get that number on the left-hand side. We get that negative number on the right-hand side. Take the negative number over by adding, and this time we get a normal force of 5.89 times 10 to the 4. It's bigger than the normal force at the top. We would expect that every single time. Every single time. Out of 10 times, we do a question like this 100 times, we would expect the number at the bottom to be bigger than the number at the top 100 times out of 100. It has to be bigger. It's kind of like in a tug of war. You're in a tug of war here. Okay, if you're in a tug of war and everybody, you know what we're like now, right? Everybody gets your participation ribbon. No winners and losers. So you're in a tug of war, and the boys grab one end of the rope, the girls grab the other end of the rope, and then you just kind of turn around beside each other and both pull in the same direction. So the rope is being pulled like this. Okay, boys are pulling like this, girls are pulling like this. Okay, it's all nice. Let's be nice to each other. Nobody wins, nobody loses. Okay, that's like when we're at the top of the circle, right? We're both pulling in the same direction. But at the bottom of the circle, we got a real tug of war. That way it should be. We got a real tug of war, and the boys are pulling one way, and the girls are pulling the other way. Hey, notice the girls are pulling harder than the boys there. When do the girls have to pull harder? Well, the girls have to pull harder when they're pulling against the boys, right? When they're pulling in the opposite direction. When you're pulling in the same direction, the girls don't have to pull nearly as hard. Same deal here. When normal force and gravity are in the same direction, the normal force doesn't have to push as hard. But when the normal force is opposing gravity, like the real tug of war, then the normal force has to pull harder, just like the girls would have to pull harder in that tug of war. C, determine the apparent weight of the car when it's at the bottom of the loop. This was a one-pointer. And it was just a one-pointer because all I wanted you to do is recognize that apparent weight is exactly the same as the normal force. Now, I didn't ask you this on this unit assignment, but I have asked you a few times on your amusement park assignment to find the number of G's. So let's do a little off to the side over here, because you are asked this in your your field trip assignment a few times. How would you find the number of G's here? My apparent weight, my normal force, whatever you want to call it, is 5.89 10 to the 4. How would you find the number of G's? Yeah, JC? Good. We're going to say Fn divided by Fg. So in this case, it would be, I don't have my unrounded number, but that's what we really should use, right? Is my unrounded number there? I just don't have my unrounded number because there were no more questions to do. Divide that by the force of gravity, which is, well, 1,200 times 9.81. Let's see what that ends up equaling here. (5.89) times 10 to the 4 divided by 1,200 times 9.81 gives me 5.00, eh? You could just say 5.00, or you could say 5.00 G's, either one. So you're going to start probably passing out at the bottom of this roller coaster at 5.00 G's. Expect that number at the top of the roller coaster to be smaller, right? Because your apparent weight is less, so the G forces you would experience would be less. So this wasn't part of the assignment. I don't remember, to be honest, if it's part of tomorrow's test or not. I don't remember if I asked you that or not. But I do remember for sure that I have asked you that a few times on your field trip assignment. 3, determine the gravitational field strength produced by Jupiter at a point on Jupiter's surface and 800 kilometers above the surface of Jupiter. We had that data on the very front page. They gave us masses of planets and the radius of planets and the orbital radius of planets and so on, including the mass of Jupiter. I'm just going to write that down here so I have it, as 1.90 times 10 to the 27 kilograms, and the radius of Jupiter as 7.15 times 10 to the 7 meters. Now we want to find the field strength. Field strength, right, is G. It's not F, it's little g. Okay, be careful. On your unit test, at one point you're asked for gravitational field strength. And with the wording of the question, traditionally on that question, a lot of people mess up on it and solve for force. Okay? Know what you're being asked for. Read the question, know what you're asked for, and then solve for what you're asked for. If you solve for force, or if you're asked for force or weight, same thing, then get F, gm1 m2 over r squared. If you're asked for field strength, then don't get force, get field strength. Now, the field strength here is gm over r squared. So we're going to say it's 6.67 times 10 to the minus 11 times the mass of the producer, because we have the mass of Jupiter here, is 1.90 times 10 to the 2. 27, yes. That would be a light planet, actually, wouldn't it? 10 to the 2. 190 kilograms. Like, there's people that weigh more than that, for heaven's sake. 10 to the 27, thank you. Divided by r, 7.15 times 10 to the 7 meters. And again, here's where a number of people messed up on this. Square that. Square that. And when we do, we end up getting 24.8. Lots of people messed up on the units as well. It's not newtons. What would it be? Maddie, what would it be? Yeah, it would be, you say newtons per kilogram, that's the most common unit we'd use, but you could have said 24.8, what else? Meters per second squared, because gravitational field is the same as acceleration, right? So typically, because of the context of this, newtons per kilogram, but meters per second squared would also be correct. Now, what do you got to watch out for in B? The gravitational field strength 800 kilometers above the surface. Yep. Yeah, the fact that it's kilometers and the fact that it's above the surface, right? Both of those things. So that means that we're going to do pretty much the same thing, but we've got to be careful to use the right R. The value of R should be 7.15 times 10 to the 7 plus 800,000. And then it's all got to be inside brackets, and then you got to square that total distance from this point above the surface to the center of Jupiter. And when we do that math, we end up getting 24.2 newtons per kilogram. Some of you get the same number, 24.8. Of course, we would expect the field strength to be less, right? You're 800 kilometers up. The field strength is going to be lower. Although, as you can see, it's not that much lower. Not as much as maybe you'd expect. 4, the gravitational force. Now we're looking for force. Okay, some of you found force in number 3, looking for field. Number 4, now we're looking for force. Now there's a couple ways to do this. What's one way? What's one way to find the force of gravity? Sarah, how did you find the force of gravity there? Okay. Yep. That's exactly what I expected most people to do, and it is absolutely correct. 6.67 times 10 to the minus 11 times both masses, 300 kilograms times the mass of Jupiter, which is 1.90 times 10 to the 7, divided by R, which is, once again, 7.15 times 10 to the 7, plus 800,000. When you do that, you get 7.27 times 10 to the 3, and the units for this are newtons. Now, how many people did it a different way? Yeah, what'd you do, Dylan? Yeah, you could also use F is equal to m times g. Remember what we said the problem with that equation, or with that equation is? The problem with it is, if we don't know the value of g, if it's not 9.81, how do we use it? Well, we do know the value of little g. It's not 9.81, but we just found it. It's 24.2, or it's actually 24.2439, the unrounded number. And the mass we use is not the mass of Jupiter. We use the mass of the experiencer, which is the 300 kilogram UFO. Lo and behold, when we do that, we get the same number, 7.27 times 10 to the 3 newtons. So either way is fine. Okay, the second way is a little bit shorter, but no better. Five, the International Space Station orbits the Earth, around the Earth at an altitude of 360 kilometers above the Earth's surface. What's the speed and what's the time that it takes to make one revolution? What do we got to watch out for here? A couple things. Peter, what's one of the things we've got to watch out for in this question? Yep. Kilometers, we want meters, of course, right? What's another thing that we got to watch out for, Christine? Yeah, good. It's above the surface, and of course, we always want from the center of the Earth here. It's a satellite problem, and in a satellite problem, we say FC equals FG. Centripetal force equals the force of gravity. R's cancel. One of the m's cancels as well, so we're left with v squared is equal to gm over r. What m do I have left? The mass of the space station or the mass of the Earth? Well, we only have one mass, right? We only have the mass of the Earth. But man, I could envision a time where you would see a question where you're given the mass of the space station and the mass of the Earth. Okay, and then you're going to be like, oh, which one do I use now? Okay, remember the mass of the satellite. This is the mass of the satellite or the space station, and then there's both masses here. So the mass of the satellite or the ISS ends up canceling. We're left only with the mass of the Earth. So let's sub some numbers in here now. V becomes, by the way, equal to the square root of gm over r squared. R here ends up being 6.38 times 10 to the 6 plus 360,000. Put it in brackets and square it. Well, that's if you probably calculated that number first and then subbed it in. Whatever works though. We get V is 7680. Let me rewrite that so you can read it. 7680.3496 meters per second. That's like 8 digits. Why did I write down the unrounded number? Alexis, why did I write down the unrounded number there? Yeah, odds are I will need it in question B, right? But the rounded number to 3 digits is 7.69 times 10 to the 3 meters per second. And the time that it takes the ISS to make one revolution around the Earth? What is that called, the time that it takes to make one revolution? Yeah, it's the period, right? Now, Matty G, how am I going to find the period? of the ISS making one revolution around the sun? Or the Earth, sorry? Good. V is equal to 2 pi r divided by t. Rearrange that. T goes up, V goes down. 2 times pi times r, which was 6.74 times 10 to the 6. It's these two numbers added together, right? Divided by the speed that we just found, 6, the unrounded speed, gives me 5.51 times 10 to the 3 seconds. I think everybody solved for it in seconds, but if I had asked for the period in, let's say, hours, what would we have done? You could have done it in hours here because it didn't specify, right? Hours would have been fine, but I don't think anybody did that. How would you change this to hours if you were asked for the orbital period in hours? What would you have done there, Max? What would you have done to find the orbital period in hours? Okay, 60 and 60 again. Good. Except it's not times, because if you times it, you're going to end up with a gigantic number, right? So if you end up with 5,500 seconds, you're going to end up with less hours than you had seconds, right? So if it's not times, it's right. Times gives you a bigger number, divide gives you a smaller number, and intuitively we know we want a smaller number, so we'd end up dividing by 60, as Max said, and then divided by 60 again. 60 to get minutes, and then 60 again to get hours. Or some of you may remember a one-step one for that. What is it? What is it, the one-stepper? Yeah. Divide by 3,600. But it gives you exactly the same thing, so it doesn't matter which one you do. And 6. 3 objects are placed in a row. 100-kilogram object on the left. 150-kilogram object to the right of that one. And it's 10 meters to the right. And then we have object number 3, which is 10 meters again to the right. And it's 160 kilograms. We want to find the net force on the middle one. Which way does 1 act on 2? Push or pull? Ryan, does 1 push 2 to the right, or does it pull it to the left? Pulls it to the left. I'm going to call that F12. Some of you guys called it just F1, whatever. Whatever you want to call it, doesn't really matter. What about 3 on 2? 3 on 2. Who haven't I called on today? Who haven't I got today? I'm looking around. Luke, I don't think I've called on you. Force of 3 on 2 is which way?
Point to the right.
Yeah, 3 is pulled to the left, but I don't really care about that, right? Force of 3 on 2 is to the right. Now let's get both of those forces. So 6.67 times 10 to the minus 11 times 100 times 150 divided by 10 squared, not 10, but 10 squared, gives me 1.0005 times 10 to the minus 8 newtons. And then the force of 3 on 2, so all 4 in a really similar way, 1.6008 times 10 to the negative 8 newtons. And then we say, just like back in our vertical circular motion problem, question number 2, when we have more than one force acting, we would say, Caitlin, we'd say F net is equal to? Good, the sum of the forces. Not F1 plus F2, but I know what you mean there. Both forces that we have here, F12 plus F32. Now, usually we'd say M times A or MV squared over R. Grayson, what do we got to be careful of when we add these up? Yeah, which one's negative? I made the other one negative, actually, because it's to the left. This one's to the right, this one's to the left. But in the end, as long as you make one of them negative, like that's the most important thing, right? So I'm going to make negative 1.0005, but it could work to do the other one as well, as long as this one of them is negative and one of them is positive. That gives us 6.00 times 10 to the negative 9.